thank you for coming to a new seminar series, the second one in this series. St. Michael's College presents Solutions for Social Impact. Today I'm delighted to introduce the physics professor, Dr. Alain Brizard. Dr. Brizard comes from Montreal, Canada, and he has earned his PhD in astrophysics from Princeton University, where he did his degree between 1985 and 1989. He then moved on for a postdoc to California at the Lawrence Berkeley National Laboratory and the University of California, Berkeley, where he did his postdocs from 1989 to 1994. He arrived at St. Michael's College in the year of 2000 and was promoted to full professor in the year 2012. He is the author of over 100 peer-reviewed presentations, which is an achievement. And he will present to us today on a new approach to renewable energy resources that are carbon emission-free. And he will present together with his senior physics students, Brooke Hotchkiss. And here is Alain Brizard. Thank you.
Thank you so much, Ruth. This event is also sponsored by Uplift. And let me read briefly a statement from Uplift. Thank you for attending this Uplift qualifying event. Uplift encourages and supports programs that promote self-awareness, understanding, and cultural competency. We want our students to live honestly, respectfully, and inclusively while doing well and doing good. This program today provides an opportunity for you to learn and grow in global citizenship, interpersonal development, and or personal wellness. Students are encouraged to snap the QR code, I believe it was in the back of the room when you entered, to track attendance and automatically be entered into the Uplift prize drawings at the end of the semester. Prizes have included items like gift cards, a free parking spot, game systems, dinner with Father Brian, a senior week ticket, and much more. The more Uplift events you attend each semester, the more chances you have to win. As a precursor to the bigger prize drawing at the end of the semester, we'd like to thank those of you who are here tonight by giving away 3 small prizes to a few lucky winners. Oh, there it is. Well, welcome. My name is Alain Brizard. I'm a physics professor, and what I'd like to tell you about today is that in the face of climate change, in a face of an energy crisis, there is hope. And there's even hope that it's going to work. So the title of my talk is Creating a Star on Earth, how nuclear fusion can play a role in a carbon emission-free future. So on the left here, we have a picture of the sun, taken probably in ultraviolet. That's why the sunspots are bright. The idea here is to put the sun in a bottle on Earth. So this is the bottle. So this is a nuclear fusion reactor of the type called tokamak that I'll talk about later on. So the nuclear fusion reactions take place inside the reactor. Neutrons are emitted and basically allow water to become steam. The steam causes turbines to turn, and voila, we have electricity. So ultimately, all electric power generation, the goal is to produce steam so that turbines rotate and generate electricity. So tonight, I'm going to focus my attention inside the reactor. So brief overview of the energy crisis scenario. On the left here, we have energy consumption in billions of barrels of oil equivalent per year. So billions of barrels of oil equivalent is no matter what type of energy you use, wind, solar, geothermal, there's a number associated with it. That's an energy in joule. And then we put this number of energy in joule in billions of barrels of oil. So we can see here, as the world population grows and as the world population modernizes, namely acquires more energy-intensive lifestyles, the demand in energy will continue to grow. The plateau here is under the assumption that the world population will level off at about 10 billion people. You can see that at about 2050, there's going to be an energy deficit, as energy available from fossil fuels will decrease, reach a maximum and decrease. As you can see, starting in 2050, in merely 30 years, we'll go into an energy deficit. So the year 2050 is a magical year. If you read reports from the IPCC about climate change, all the goals are often set up in terms of that precise year. We see also that 2050, hopefully, the reliance on fossil fuel will decrease. And then we see at about the same time, renewable energy, nuclear fission, if we're able to increase its use, there's still a deficit in energy at about 2050. So we have two options. Either we change our lifestyles, we go back to more moderate energy intensity, or we allow everybody to adopt these energy-intensive lifestyles, and therefore we need a new energy source. Well, the energy production based on fossil fuel has a climate impact. What we see on the right here, since 1750, we see that about 70 years ago, with large increase in populations in countries like China and India and so on, we see that we are injected massive amounts of carbon dioxide into the atmosphere as a result of the production of electricity from fossil fuel. On the left here, we look at energy, electricity production, and we see, I'm showing here the top 5 countries. Of course, the European Union is not a single country, but you can see here China and the US produce almost half of the electricity in the world, but that electricity is produced by fossil fuels. So that has an impact on the climate. Let me briefly say a few words about the relationship between climate change and greenhouse gas emissions. So I've derived a very simple model for the surface temperature of any planet in terms of the albedo, which means the sunlight reflected from the planet, as a percent, and the greenhouse coefficient. So this is a two-parameter model for the surface temperature of the Earth. T0 here is the temperature of the Earth if all the energy from the sun was absorbed at ground level and there was no atmosphere. And the graph on the right shows that behavior for a constant albedo, and I'm simply changing the greenhouse effect. Currently, the Earth has a greenhouse coefficient of 0.39, or 39%. Without the greenhouse effect, the average surface temperature on Earth would be negative 19 degrees Celsius. That's an average. The equator, of course, would be slightly warmer, and our current location at a latitude of about 45 degrees would be very cold. And that's an average temperature. That's clearly unlivable. With the current greenhouse coefficient of 39%, the average surface temperature on Earth is 15 degrees Celsius, a little bit below 70 degrees Fahrenheit. Quite comfortable. Everybody is happy with this. Venus used to be happy also. The atmosphere of Venus is dominated by methane and carbon dioxide, two primary greenhouse gases. You can see here that the temperature, the surface temperature of Venus has jumped to almost a greenhouse coefficient of 0.99, giving the surface temperature of Venus at about 625 degrees Celsius. Now, Venus is closer to the sun, so we can expect the temperature at the surface of Venus to be higher, but not that high. In fact, the surface temperature of Venus is so hot that only recently have we been able to land probes on the surface of Venus. Before that, those probes would not reach the ground. They would be essentially destroyed. So the greenhouse effect is beneficial, but not too much. And that's the key point. There are interesting feedback loops. I was explaining, Brooke, the fact that it looks like a positive feedback would be a good thing. You know, if you take a test and I give you feedback, you want the feedback to be positive, but in terms of climate, not the case. The positive feedback, let's look at the albedo positive feedback loop. Let's assume that the albedo of Earth decreases. Namely, less sunlight is reflected into space. Well, that means that solar absorption at the surface of the Earth will increase, and consequently, the surface temperature will increase. If the surface temperature increases, sea and land ice will melt. These are the prime contributor to the albedo effect. So the albedo then goes down, and the loop continues. We are under our reliance on fossil fuel, we are increasing the greenhouse coefficient. And there's also a positive feedback loop associated with the greenhouse. And sometimes people talk about the tipping point. Are we close to the tipping point? Is it too late? You can see here that this dependence on the greenhouse effect has a very gentle rise. So Earth is right here. But as you approach G is equal to 1, a slight increase in G can lead to a very large increase in temperature. That's the kind of tipping point that we're talking about. So this looks pretty bad. Is there hope? And of course, you wouldn't be here, I wouldn't be here if there was no hope. The hope here is that nuclear fusion offers a carbon-free energy source, has a huge potential. It is environmentally responsible and safe, and I'll try to convince you today that a type of nuclear energy can be safe. It uses fuel that is abundant, namely water, and it is sustainable. We have enough fuel on Earth to, through nuclear fusion, give us energy on a time scale of 1 billion years. So this is not 2050, 1 billion years worth of energy on Earth. Pound for pound, nuclear fusion gives you nearly 4 million times more energy than you get by burning coal, oil, or gas. I'll give you a few more examples, but one of the most dramatic examples of the benefits of nuclear fusion, a bathtub filled with water and a few lithium batteries will provide enough energy to supply one person a lifetime of clean and reliable energy. One bathtub. You have energy for your entire life. Well, maybe the next time you take a bath, you say, wow, there's a lot of energy in there. But, there's always a but, isn't there? But nuclear fusion on Earth requires extreme conditions seen nowhere else in the universe. Within a matter, essentially, of the distance between Brooke and myself, a few meters, we will go from a temperature of about 100 million degrees Celsius, almost 10 times the temperature at the center of the sun, while Brooke would be at nearly 0 degrees Kelvin. So those conditions are nowhere seen in the universe. So it is a big technological challenge. Tonight, what I'd like to do is to report on the progress we have made toward using nuclear fusion on Earth. So nuclear fusion involves a state of matter called the plasma. It's the fourth state of matter. As you take a solid and you add heat to it, the solid becomes a liquid. You continue adding heat, the liquid becomes a gas. And normally, people stop there, the 3 phases of matter. But if you were to continue increasing the temperature, the gas becomes ionized. And a fully ionized gas is what is called a plasma. I'll show you several examples of plasmas, but I'll give you a hint. More than 99% of the universe is in the form of a plasma. So we are, all of us, very unusual states of matter in the universe. So stars use their own gravity, their tremendous mass, to confine the plasma and to crush it under the action of gravity. That inward pressure raises the temperature at the center of the star and causes it to become hot enough to overcome the repulsion between the nuclei, the positive charges. And nuclear fusion is possible in stars, and that's the 99% of the visible universe. On Earth, we cannot recreate the gravitational field of the sun. Instead, we use one of 2 methods. We either use a magnetic field to control the plasma, to keep it long enough, to heat it, to make it hot enough so that thermonuclear fusion can proceed. So that is called magnetic fusion. And this is what I've been working on for since 1985. The other mechanism, the other approach to nuclear fusion is called inertial fusion. And with inertial fusion, you have a very small pellet containing the nuclear fusion fuel, and then you irradiate that small pellet with very powerful lasers. And then you hope that the implosion is successful in heating the fuel and keeping it long enough compressed so that nuclear fusion can begin. Some examples of plasmas around the universe. So auroras, flames are examples of plasmas. So what we have here, we have temperature. You can basically look at it as in Celsius, and the horizontal axis is number density, the number of particles per meter cube. So auroras are relatively cool and relatively not dense. As you increase the temperature, we see here neon signs. I have no doubt that all of us have seen neon signs. Well, the gas inside the neon tube is not a gas. It's an ionized gas, which is a plasma. Lightning bolts, very high density and very high temperature. It's very high temperature. You see it because it's giving you the telltale color of violet to ultraviolet. And then we continue and we see the center of the sun, very high density and at a temperature of about 10 million degrees Kelvin. The sun is able to generate nuclear fusion because of its large mass. On Earth, we cannot recreate this mass, and therefore we need to proceed to much higher temperatures. So this is an example of a magnetic fusion reactor with temperatures in excess of 100 million degrees Kelvin with densities that are comparable to the density of a neon sign. So that's pretty amazing. And then inertial confinement, again using powerful lasers, have very similar conditions. So how does nuclear energy work in comparison to fossil fuel or chemical energy? Well, let me first of all describe the comparison between fusion energy, fission energy, and fossil fuel energy. In each case, I'm using 1 gram of fuel. 1 gram of fuel of deuterium and tritium reaction will give you essentially, ultimately, 30 megawatt hour of electricity. That's a lot of light bulbs, by the way. A fission reactor, again 1 gram, will give you only 0.19 megawatt. A mega here is a million. While if you burn 1 gram of coal, you get only 3 watt hour of electricity. Another way to say this, 1,000 kilogram of coal, a metric ton, will give you the same energy that you get from burning 1 gram of deuterium-tritium fusion fuel. That is a huge difference. And that's the goal, that's the advantage of nuclear fusion. It's the highest energy density form available to us. And it's available because you're essentially tapping into the binding energy of the nucleus. In chemistry, the energy you get is by breaking the bonds of electrons. I have my chemist colleagues here. Chemistry is all about electrons. You break bonds and you create new bonds, and the difference is in the form of energy available. the binding energy of nucleus is way, 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 way more than the binding energy of electrons around nuclei. So nuclear energy can be produced either by the process of fusion, where you fuse light nuclei together to produce heavier elements. And the biggest jump is when you go from hydrogen to produce helium. That's the largest jump in energy available. But that fusion process stops at the element iron. If you want to go beyond iron in the process of fusion, instead of producing energy, you need energy. And that is not a very favorable scenario. You don't create energy, you don't create money by just always giving money. The reverse process is the process of nuclear fission, where you take a heavy nucleus and you cause it to split apart. Once again, it slides down this curve and energy is produced. But you can see here the reason why you get so much more energy by fusion than fission. You see here the very small drop, whereas you have a large drop on the fusion side. That's basically why nuclear fusion is so attractive. So a few basics if you want to construct a nuclear fusion reactor. So first of all, the fusion plasma needs to be confined at very high density. Why? Because the fusion reactions involve nuclei colliding with each other. So the more nuclei you have, the more likely you're going to have a fusion reaction. A fusion plasma also needs to be heated to very high temperature. Why? So if I have very slow nuclei moving toward each other, they each carry a positive charge. And if you think back to perhaps physics high school or college physics, those slow positive charges will repel each other way before they get close enough to feel the strong nuclear force. But if they have a lot of energy, they collide with so much energy that they get close enough that the nuclear force can come into play. That's when the nuclear fusion process begins. And consequently, you need a very high temperature. And you're putting energy into the plasma, but unfortunately, that energy is leaking. So you want the rate of nuclear fusion to be higher than the rate of energy loss. When you combine these three parameters, density, core temperature, and energy confinement, you arrive at what is called the triple product, the Lawson criterion. Don't worry about the number here, but the goal is that if you can produce a fusion plasma that exceeds that number, then you have met all the conditions for your fusion plasma to produce energy. On Earth, we do not really have access to the same fusion reactions taking place at the center of the sun. We don't have the gravitational mass of the sun. The most favorable reaction involves two isotopes of hydrogen, deuterium and tritium, which then fuse together, produce a nucleus of helium-4 known as an alpha particle and a neutron. The neutron escapes the plasma and with most of the kinetic energy, whereas the alpha particle stays behind, keeps the plasma hot enough to sustain the DT fusion reaction, but ultimately needs to be removed from the fusion plasma, because the helium is the post-reaction product. It's a little bit like a log. At some point, you need to remove ash from your fireplace. Otherwise, the fire is going to die. So these are the conditions necessary to produce a burning plasma. So brief history of nuclear fusion. In 1929, we realized that Einstein's famous formula, E is equal to mc squared, enables us to predict that large amounts of energy can be released by nuclear fusion. Hans Bethe in 1939 uses that formulation to explain how stars produce their energy. Before that time, we thought that stars produce their energy by chemical reaction. I don't want to scoff here, I have chemistry colleagues in the audience, but that process would have caused stars to die a long, long time ago. There was no way you could produce that amount of energy. Fortunately, the process of nuclear fusion is the reason why stars are producing these astronomical amounts of energy. In 1947, we say, well, that's easy peasy. Nuclear fusion, you take plasma, compress it, heat it, that should be easy. But a plasma as the fourth state of matter is very difficult to control. Fusion plasmas have once been described as trying to control a ball of jello with rubber bands. So think about that for a while. It's not easy. So these early experiments fail. 1950, Andrei Sakharov and Igor Tamm in the Soviet Union proposed a concept known as the tokamak concept. Tokamak is an acronym. Tok refers to the toroidal shape. That's the shape of a donut. And mak refers to a machine. So it's a machine in the form of a donut. They proposed this concept as a magnetic confinement fusion device. Lyman Spitzer in 1951 at Princeton proposes a different concept, a far more complex concept called the stellarator. 1952, Edward Teller begins work on the hydrogen bomb at Livermore National Lab. And if you think about a hydrogen bomb, hydrogen fusion is so hard that you actually need an atomic bomb to produce a hydrogen bomb explosion. It is hard. In 1958, in the middle of the Cold War, magnetic fusion research is declassified. Namely, the Western Bloc and the Eastern Bloc recognize we've been working in secret on each side, but we recognize that nuclear fusion is too important for humanity, that we're going to share all our secrets. When I was a student at Princeton, it was really thrilling to open documents that were just printed, top secret. Now everything, all the various approaches to nuclear fusion were declassified in 1958. You still think, you're not old enough to remember the Cold War. Well, many of you are not old enough. But the Cold War, this was the ultimate in not trusting your opponent. And here we were shaking hands, sharing secrets. Many of the scientists who attended this conference I've met, and I've heard stories of scientists meeting each other in bars and cafes, and the game was to escape your KGB handler or your CIA handler so that you could find a room and talk about physics. 1960, we think that we have found ways to build machines that can lead us to the promised land of nuclear fusion to very, very, very poor results. So the 60s are really just a bad time for nuclear fusion. In 1968, a tokamak known as T3 is built at the Kurchatov Institute in Moscow. And again, open results. Western scientists are invited to the Kurchatov Institute. I've met some of them, and describing going to Moscow during the height of the Cold War, and was absolutely fascinating. But the results are confirmed, and then these scientists come back to the West and transform every single machine into tokamaks. So that's the golden age of the tokamaks. TFR in France, PLT at Princeton. I worked on TFTR, and I also worked on D3D. JET is in the UK, is currently working as a DT fusion machine. And of course, earlier this year, there were a very important record in fusion output. JT60 is in Japan. So you can see here, there's a large number of tokamaks all around the world. 1980s, the birth of my own specialty, which is gyrokinetic plasma theory, is born. 1985, at Geneva, Reagan and Gorbachev discuss plans to build the International Thermonuclear Experimental Reactor known as ITER. I start my PhD studies at Princeton in 1985, and that very same year, Back to the Future comes out in movie theaters. And if you've seen the movie, this is a Mr. Fusion at the back of a DeLorean. 1997, the JET, which is the Joint European Torus Experiment, achieves a world record in fusion output, 26 megawatt of fusion power with an input of 24 megawatt. And we're going to introduce a fusion performance factor, which is called the Q factor, which is fusion output over heating input, and we get 0.67. Break even is Q is equal to 1. Break even means that you spend a buck and you earn a buck. So you put energy into the plasma to create a fusion-producing plasma, but unfortunately, it gives you back the energy. In 2003, the ITER Global Partnership is created. USA, European Union, Russia, Japan, Korea, China, India. If you go back to, I believe, the second slide, these are all the countries that produce the most electrical energy by using fuel, fossil fuel. So more than 50% of the world population lives in a country that is a member of the ITER partnership. So this is as global as it gets. In 2005, the ITER project so the decision is made to build ITER at Cadarache near Aix-en-Provence with the goal of producing 500 megawatt of fusion power from 50 megawatt of heating power, namely a Q of 10. I was there in 2009, and the ITER field was still, populated by wild pigs or sangliers. It's really just amazing to see them. Now it looks very different. 2022, this year, JET has a record amount of fusion energy produced, and those results are exactly confirm the theoretical predictions of how JET would perform. And therefore, we know we're well on track in our ability to predict how ITER will function. ITER is expected to enter its DT operations in 2035, and there are already plans of many countries around the world to start building their own demonstration fusion reactor with a goal of Q of 25. So two very different magnetic configuration scenarios. Brooke and I are this summer studied the tokamak concept, and Brooke will say a few words about his study this summer. And our plan this semester is to look at the stellarator concept, which has been built in Greifswald in Germany. This is called Wendelstein 7X, and it produces both what are called toroidal magnetic fields and poloidal magnetic fields with a very different type of coils. In fact, I was in Greifswald in 2003, and the machine was completed, I would say, 2016. It took 13 years to build the machine. In fact, building a stellarator is so difficult that Princeton attempted to build a stellarator about 10 years ago, and they abandoned the plans because it was too difficult. It was too costly, really. So this is described as the machine that was built in hell. The precision of how you tailor those coils is unbelievable. This is the size of this room, and the precision has to be well within a few millimeters. It is an amazing machine. I was there 5 years ago, and it is quite amazing. So I've talked about the triple product. So this is the NT tau product. This is the core temperature. And so we want to go and, so ITER is designed to operate in this region, well within Q is equal to 1. And all of those machines here, essentially, many of the machines have died. They're no longer in use, but it shows you the progress. These machines are built all over the world. And for the past 40 years, 50 years, almost the entire humanity is working on solving the problem of nuclear fusion. So this is what ITER will look like. It's a tokamak. The plasma will sit inside this toroidal chamber. Just to give you an idea of scale, this is a human being. Let me see if I can play the video. This is a fly-through. Maybe it's not going to work. So this is what happens when you have a sophisticated Mac in a world of PCs. So ITER now is understood. It used to be International Thermonuclear Experimental Reactor. Now ITER is the way in Latin. We need to understand the physics of burning plasmas. We need to better control the leakage of particles and energy. Again, controlling a ball of jello with rubber bands. And for this purpose, you need to develop advanced numerical plasma simulation techniques. And that's where I come in. Sometimes I describe myself as an equation whisperer, and code developers around the world use my equations in computer codes so that their codes operate 1,000 times faster. So you turn a job that would require a year of a computer program running, and now you can run it in 3 hours. And that's what a factor of 1,000 looks like. How do we understand the current tokamak plasmas? Are we able to understand what is going on? The vertical axis here is the measured confinement time for all of these experiments, and the horizontal axis is the predicted confinement time. And I don't have to tell you, but the slope here is 1. But the idea here is that these are all the tokamaks that we've operated in history, and here's ITER. So it looks like we're on track, but the gap here involves a type of physics that we know very little about, the physics of burning plasmas. You may have read in the news that nuclear fusion is very popular. Fusion research has attracted many private companies. So these are all the companies that are trying to rush toward building a nuclear fusion reactor. A nuclear fusion reactor for the purpose of producing energy. ITER is not designed to produce energy. It's not designed to produce electricity. These companies have decided to invest millions and billions of dollars to build a nuclear fusion reactor as soon as possible. One of the more promising companies is a spin-off of the research group at MIT called the Commonwealth Fusion Systems, and they have built a concept which uses what are called high-temperature superconducting coils. Here, superconducting coils are a key component of any future nuclear fusion reactor. So SPARC is their prototype, a very large magnetic field, and consequently, with the same fusion performance at ITER, would be about the size of a few meters in size, whereas ITER is a gargantuan machine. So the hope is that SPARC will be successful and will be the prototype of a final or a first fusion reactor called ARC with a Q of around 50. So fusion could be right around the corner. If any of these companies find a way of turning a plasma into a fusion energy producing plasma. So the physics of magnetic confinement, and this is when I'm going to ask Brooke to explain a little bit what we're going to be seeing as an animation on the right. So let me start it. You can probably speak right here.
Okay. Yeah, so, okay, so you can see that the particle is, so the line in the middle in green is a magnetic field line, and the particle, the way it moves is that it orbits about a magnetic field line. And the reason that we're looking at single particle motion is that before you can understand a collection of, say, 10 to the 20 particles, you need to know that your machine will confine a single particle. And so this is the basis of how a particle is going to move in a magnetic field. And then you can complicate the geometry and look at different magnetic fields and whether or not they confine a particle.
So these machines then are designed, the magnetic field, the magnetic configuration is designed to confine particles. If your magnetic field is unable to confine a single particle, game's over. You're not going to confine a billion particles. So many of the development of fusion magnetic machines rely on single particle dynamics. And then you look at whether the plasma can be heated to fusion conditions, and you want to know whether the plasma is stable. Think of a ball of Jell-O with rubber bands, but now the ball of Jell-O is jiggling. So magnetic confinement under turbulent conditions over long time scales is very different to achieve numerically. So my specialty is what is called reduced plasma dynamics. How can you take physics equations and to produce reduced physics equations that contain the same physics, but you've eliminated some fast timescales. And so namely, your code, instead of taking an hour, would take 4 seconds to run. If you think that that's great, imagine now that you have 1 billion particles. So improvements in the speed of computation is a very large key. There are 2 approaches, guiding center dynamics, which Brooke and I worked on this summer. He'll be able to say a few words about this. And then gyrokinetic and gyrofluid dynamics is what you need to really consider burning plasma conditions. For the purpose of studying these burning plasmas, several improvements have been made over the years. Computer improvements are shown by this curve right here. This is simply improvement in hardware. What you see in red and in green, you see the quantum jumps, the recognition that we can do the same physics but better by applying sophisticated mathematical techniques. We will need even better mathematical methods in order to describe burning plasmas. So guiding center theory have been an architect of guiding center theory for many years, culminating in a review paper in 2009 with my colleague John Carey at UC Boulder. So this paper has already received 350 citations. So Brooke will tell you a few words about what you're looking at. This is work that was published with an undergraduate student at St. Mike's, Danielle Markowski. She's now a graduate student in space science at Clemson University.
Okay, so the figure to the left, so we're looking at a single particle motion and the magnetic field of the Earth in this case. And so to the left, you see the full particle motion based on the full physics. And this is a computer simulation. And so the way the particle is moving, it's spinning or gyrating about the magnetic field line. It's bouncing up and down vertically. And then there's a slow precession motion going around the Earth. And those are the 3 directions of motion. And what takes the most time in your computer simulation is the fast gyro motion that Dr. Brizard is highlighting within a bounce. And so to the right, you can see for the same particle, you use the guiding center approximation. You remove that motion. That approximation makes your code run 1,000 times faster, and you essentially you still keep the bounce motion and the precession motion around the circle, but you've eliminated that fast gyro motion that wasn't really, so you follow the particle, but you do it faster, and you get essentially the same results.
So this is your work. This is work done by Brooke last summer, funded by a grant from the National Science Foundation. So this is now a particle orbit in a tokamak magnetic field.
Yeah, so we were looking at kind of a more simplified version of a tokamak magnetic field. And so in blue, we show the orbit of a particle, and then in red, we show the guiding center orbit, the approximation. And you can see that it's more complicated in this case, the motion is, but there's still the same elements. So you can see in red the guiding center, and in blue the particle is gyrating or orbiting. It's kind of spiraling around that orbit. There's still the bounce points where the particle's bouncing, and then there's still the same precession around in a circle. It's all just more complicated and more overlapped.
Thank you. So now if we include plasma turbulence, this is essentially the jiggling ball of jello. You can still apply the methods of reduced plasma dynamics, but now to include plasma turbulence. This is a review paper I wrote in 2006, 2007. This has received more than 1,000 citations. This is the paper that forms the basis, the theory basis of all the gyrokinetic computer codes around the world. I've lectured around the world on gyrokinetic theory. I wrote an extensive set of notes, which I presented the first time at the Los Alamos National Lab in 2013. And during a sabbatical, I gave a 2-week course in Hangzhou, China, at the Institute of Fusion Studies. So I'm not going to run the code, but essentially, this is what happens when you have plasma turbulence. So the particle can be led to leak out of the plasma very quickly. And what you want to do, you want to control that turbulence in a way that keeps the particles inside the plasma and the energy inside the plasma. So it's a very, very, very complex problem. But if you were to do this with Newton's equations of motion, it would take years to complete a numerical simulation. With gyrokinetic equations, which are based on the guiding center theory, you can do this much faster. So roughly speaking, this is how a fusion reactor would be built. There's the fusion plasma inside. Deuterium is fusing with tritium, producing a neutron. The neutron escapes. Surrounding the plasma is a liquid metal wall made of lithium. The purpose of the liquid metal wall is to absorb the neutron, get hotter. The hotter liquid metal is then allowed to transfer its energy to water. Water becomes steam. Steam causes a turbine to turn, and you're producing electricity. The great advantage of the lithium blanket is that lithium can, by absorbing the neutron, can produce tritium, and the tritium then can be recycled into the plasma. To heat the plasma, there are two main methods. The first one is to inject neutral particles inside the plasma. As they penetrate the plasma, these neutral particles ionize and become trapped by the plasma. So that's called neutral beam heating. The other approach is to use radio frequency waves. Essentially, you treat the plasma as a microwave oven. The safety of a deuterium-tritium fusion reactor: if any equipment failure occurs, that immediately leads to plasma extinguishment and the reaction dies. You cannot have a meltdown. Fusion is hard, so fission is easy. So if you remember something from tonight, fusion is hard, fission is easy. I'm not saying anything about chemistry. The reaction products, helium and the neutron, completely not radioactive. We're not dealing with the radioactive fission products of fission energy. The neutron is absorbed by the reactor structure, and it's the neutron absorption by the reactor structure that produces a radioactive metal structure. So iron, for example, absorbs a neutron, becomes iron 58, still stable. Absorbs another one, iron 59. Iron 59 is radioactive, has a half-life of a few seconds. It becomes cobalt 59. But these are low-level radioactive elements. And this is a solid reactor. It's not going to fly away. And we have limitless resources, namely deuterium is abundant on Earth. It has about 34 milligram of deuterium per liter of water. So there's a lot of fuel on Earth. So a few words to conclude about fusion research at St. Michael's College. I've involved over the years physics students. Brooke is a very good example of that student involvement. We have created in the physics department a unique program of junior and senior physics seminars, so that students in the physics program do research the last 2 years of their time at St. Mike's. So they are really well acquainted with research. This is not solving problems from a textbook. This is actual research. I've had the great privilege of being supported financially by the National Science Foundation and the U.S. Department of Energy over the past few years. I have active collaborations around the world, and this is my final slide. And perhaps you recognize Sheldon and the famous whiteboard. I have a colleague at UCLA who is the science advisor to the Big Bang Theory. And this is a board that contains equations associated with gyrokinetic theory. This is legit. So sometimes people ask, are the whiteboards legit? Yes, they are. So thank you for your attention. And any questions? Yes.
Is the gyrokinetic theory complete, or is there another quantum step to get the simulation speeded up?
Yes. So would you mind repeating the question? Because that's what I'm working on right now.
Yeah, is the gyrokinetic theory complete, or is there another way to speed up the simulation?
There's a great scene in The Godfather 3. Al Pacino is in the kitchen, and he's basically saying, every time I think I'm going to get out, or something like that, they pull me back in. Gyrokinetic theory was my PhD thesis topic 35 years ago. And I thought, all right, I'm going to be done. I've written all there was to write about it, and here I am, 30 years later, still working on it. What we're trying to do right now is that the way you simulate a plasma is that the plasma is a combination of particles and electric and magnetic fields. So the way we do this is that we push the particles with the fields. These particles now become the sources of the fields. So you always push particles, advance fields. Push particles, advance fields. That's slow, because that requires moving information inside a computer. If you know anything about computers, anytime you access, you put information in memory and you retrieve it, that takes time. So I'm working on a way to advance the particles and the fields at the same time. There's a beautiful theoretical structure. That's what we're working on with colleagues at Los Alamos and in Finland. So yes, it is possible. It is possible to speed up gyrokinetic even more. Great question.
I just try to get an idea of how many people you can supply with energy with one of those machines. If you, for example, compare this to a nuclear power plant.
So the basic idea, the typical scale of an electric power plant typically will be at least 1 gigawatt, could be a bit more. So it really depends. 500 megawatt will typically be the smallest scale. Spark, the Commonwealth of Fusion Systems, the offspring of MIT, wants to build small, even smaller scale nuclear fusion reactors. So if they're successful in their model, we could have any size fusion reactor. You could have a fusion reactor on campus. I don't know if it's in the plans, Jeff? No? But I doubt it'll be a Mr. Fusion.
So one follow-up question I have, you said that some of them are already out of service. What is the average lifetime of one of those machines?
JET was built in the early 90s, and it's still around, and it's still kicking. In fact, JET started, the Joint European Torus started DT reactions, and because the JET machine itself has become radioactive, any repairs are done by robots. And those robots really are, of course, manipulated by humans. So I think JET is going to be around for at least a few more years, if not 10 years. So the lifespan is, if you have a good experiment, D3D in San Diego has been around since the 80s, and it's still kicking around.
I have a question about sociological research. Are there scientists doing research into what the effects of this will be when it's successful on society, on global trade?
What do you mean,
industry?
when it's successful? Well, we have the prospect of abundant energy. Water essentially exists everywhere on Earth. So there's no longer going to be countries that control the source of fuel. Because the research is done by almost 50% of the world population, that technology is going to be readily available as soon as it starts to work. They have access to all the data, and because the research is also funded by the IAEA, the International Atomic Energy Agency, those results will be made available to every country on Earth. So the social impact of abundant, clean energy is amazing. And I've had the great fortune to work on this problem for nearly 40 years. And I'm seeing the light at the end of the tunnel. This is exciting. The work is tremendously rewarding. And my ability to talk to students like Brooke, and I see some of my students, first-year students here, another senior student, is exciting. I cannot imagine if you're a young student and you want to solve one of the most important problems in the history of the world. Get involved with nuclear fusion. We need chemists. We need engineers. We need scientists of all sorts. And as you can see, the number of companies involved looking for young talent. Unfortunately, there are not too many physicists. We need way, way, way more physicists and engineers. So this is a great time to become a physics student. I don't know why you would decide not to be a physics student. This is so exciting.
We have door prizes for students with questions.
Ooh. All right, Max.
I was wondering about one of the questions asked early on. One of the points that was made is that we are producing more energy, but we're also using a lot more resources. The continued goal of getting nuclear fusion and having clean energy produced that way, are we going towards that goal fast enough to avoid an energy crisis?
If the Commonwealth of Fusion Systems is right, maybe fusion will be 20 years in the future. ITER will start DT operations in 2035. So we're looking at, so this is an experimental reactor. It's not going to produce electricity. But at the same time, all around the world, countries are already planning commercial nuclear fusion reactors. As soon as ITER says, yep, we're good to go, this works, then you can be sure within a few years, those commercial fusion reactors will be ready to go. China, I was in China a few years ago. They have their plans for their own demonstration fusion reactors. It's amazing. You get in the room and you see thousands of physics students, all eager to solve the problems of nuclear fusion. We need that level of excitement. This is a far bigger project than going to the moon, in my opinion. And going to the moon is nowhere near as hard as achieving nuclear fusion on Earth. I'm going to back off here, but you get the idea.
Any other questions? I'm going to go with, and I'll come back.
You said that with a bathtub full of water and a couple lithium batteries, you would have power for life. How does this impact, like, the resources of drinkable water, or like, could you use ocean water for this? I imagine that you have a byproduct of some amount of salt or something, but.
Yeah, there's a lot more seawater than fresh water.
Yeah.
We don't need fresh water.
Okay.
We don't need fresh water. We may run out of bathtubs.
Any other questions?
We've been promised fusion for about, it's 30 years away for a very long time. I heard you say 20 years for one of the machines. So are we 20 years now away, or are we 30 years away, and can you promise?
It's easier to predict the past and the future. What you can see here, we've definitely been marching toward nuclear fusion. There's no denying that progress was made. There is a joke out there that nuclear fusion is always 30 years in the future. In fact, it's a little bit like a point on the horizon. Everybody can see it. There it is. There's the point on the horizon. As soon as you march toward it, what happens? It recedes back. It's always at the same distance. That's no longer true. That's no longer true. We have made, so JET has produced a world record in fusion energy. This is, if it had been connected to a reactor, we could have produced energy, electricity. The National Ignition Facility at Lawrence Livermore has recently achieved a shot that has exceeded break-even. So we have produced energy. So I think that the joke is no longer true. It is going to happen. Nobody is laughing here. We're talking about billions of dollars of investment in making sure that we build a nuclear fusion reactor, not in 30 years, probably not in 20, and Spark is hoping it's sooner than this. So it's going to happen. And I dare say in my lifetime. Ooh. Yes, yeah. So 2035 is still well before 2050 when we start literally running out of energy. Yes.
Dr. Frank, this is terrific. What do you predict will come first, quantum computing or nuclear fusion?
Some of my colleagues have looked at quantum computing as a way to accelerate those computations. Now, quantum computing is still early. It's still involved in the game of, solving encryption codes faster than classical machines. I have not yet seen quantum computing used to solve physics equations. So quantum computing for people in the audience, regular computing, essentially a computer-based uses a binary system, zeros or ones. Quantum computing, in a way, takes any numbers between 0 and 1. So you work by using the laws of quantum physics, and surprisingly, quantum algorithms can solve problems way faster than classical algorithms. And that was a big shock to the cybersecurity industry, that you had encrypted keys that seemed to be impossible to solve. And quantum algorithms were able to to resolve these codes in a matter of minutes sometimes. So there's still a lot of progress to be made. So there's a difference between a quantum algorithm, which exists already, and a quantum computer. I suspect your question was about a quantum computer. I'm not a betting person, but I would say nuclear fusion is going to be first. Unless you're involved in quantum computing and you'll say, aha, I'll take that bet. Yes. One moment.
Thank you. Your research has to do with containing the reaction itself. Does the technology already exist to commercially take the heat produced by that, transfer it through the lithium blanket and produce electricity, or is there still a lot of work to do metallurgically?
There's still a lot of work to be done. My research is primarily involved with transforming real physics equations that if you were to build a computer code with these real physics equations, it would take years to get an answer. Now, if you're an engineer that is waiting to build the machine tomorrow, you can't wait a year to get the answer. Is this the right position for that coil? If you use, instead of the real physics equations, if you use the reduced physics equations that I've derived, then your code can run 1,000 times faster. You're going to get your answer in a few hours. Then the engineer can make the decision, yes, that's the right place for the coil. So as I said earlier, I'm an equation whisperer. I've once said to someone, I resent the implication that I ever solved anything. I derive equations that are useful.
Do you know where they are at commercially in producing the other portion of the reactor,
So
like Commonwealth Fusion and the others? Have they?
So all of these companies at some point in their design have used gyrokinetic codes, and therefore they've used some of my equations. They've definitely used guiding center codes to know whether their machine is successful in confining those charged particles.
Do you know if any of these companies are publicly held?
These are all, well, I don't know if they're on the stock market. Maybe some of them are. I know for a fact that Jeff Bezos is a major contributor to CFS, and General Fusion is in Vancouver. I have a colleague who has recently been hired by Zap Energy. So I don't know if they're traded on the stock market, but these companies were first started with venture capital. Many of these companies, so where's one, let's see here. Oh, HB11. This is the fusion of hydrogen with boron. A much harder fusion reaction than deuterium-tritium. The advantage of HB11 is that it produces no neutrons. So you do not activate the reactor. It's a completely clean reaction. But we study very speculative reactions just because the payoff is so huge. That's what venture capitalists do. They look for ways to spend their money, I guess. So many of those companies are looking at a very specific direction that is very speculative, and the payoff can be huge.
I think we'll take one more question.
Well, I was wondering about, like, what is the cost to establish these, especially with the smaller, newer ones? And then also, like, what is the maintenance going to be like on these? Like, will they be very reliable? Do you think they're going to have to, is that going to be a large chunk of that? And compared to, like, how much energy they can produce, things like that?
I'm certainly not an expert in the commercial side of and the how you can before I go on, the price of electricity by kilowatt hour right now for most Vermont resident is around 15 cents per kilowatt hour. A 60-watt light bulb left on all day has used 1.4 kilowatt hour. So around 20 cents. So electricity is cheap. The cost comes at the carbon dioxide emissions. So the cost of electricity when, let's say, CFS creates a commercial nuclear fusion reactor, I suspect the cost per kilowatt hour is not going to be 15 cents. It could be $1, could be $2. And then you say, wait a minute, no, I can't spend $2 for a kilowatt hour. But the price of electricity produced by fossil fuels can only go up. And at some point, as you develop the nuclear fusion technology, the cost of electricity will go down. But you can't have that process take place when you need it tomorrow. You need to produce electricity at $2 a kilowatt hour now, so that when you need it in 20 years, in 2050, now it's 30 cents a kilowatt hour. Whereas the fossil fuel-based is at $1 a kilowatt hour. An important element in this economics is to put a price on carbon. All right? If the consumer sees that there is a price in carbon, then progressively we're going to move away from fossil fuel. So your question really involves not only technological sides, commercial sides, and economical side, societal side, and so on. We're already seeing that we cannot continue using fossil fuels. Earth is at stake. We do not want to become Venus.
Yeah, thanks. And then also, I was wondering, just like quickly, what are some of the other different reactions that you're doing? You mentioned the DT and the helium boron, but what are there any other ones that seem possible?
Yeah, there are several. I don't see anything. So yeah, there's the ideal reaction is deuterium-deuterium, because then you're not using tritium, which is a radioactive isotope of hydrogen, and deuterium produces electrically charged products. So you can directly convert energy into electricity. With the neutron, you heat the lithium blanket It gets hotter, it's in contact with water, the water heats up, produces steam, causes a turbine to turn, and voila, you're producing electricity. Direct conversion is really the goal here. But you cannot decide to build a deuterium-deuterium reaction now. We don't understand the physics of burning plasmas. We can achieve a burning DT plasma. Let's understand the burning plasma physics, and then perhaps nature has always been kind and might reveal a secret shortcut and say, now we know how to achieve deuterium-deuterium. That's the goal.
Cool. Thanks.
This will be our last question. We're a little over time.
Has our lack of understanding in some parts of quantum physics, like maybe quantum gravity, hindered efforts to build like nuclear fusion plants? Or could a better understanding possibly help our creation of them?
All right, so I don't think we're going to get large enough masses to involve general relativity, certainly not quantum gravity. Just as a side note, it is often said that particle physics, general relativity, and so on, present the ultimate sophistication in physics theories. Not true. Some of the developments associated with pushing particles and fields together involves mathematical structures, physical theories that are so beautiful, so intricate that it makes general relativity seem simple. And nature has found a way to allow us to discover these beautiful theoretical jewels. And I would be able to go toe-to-toe with any theoretical particle physicist who's involved in superstring theory, and we could compare notes. I hope I answered your question.
I think we'll have to end it there, but I want to thank you, Dr. Brizard and Brooke, for a wonderful evening. I think we all know a little or a lot more about potential energy future. So thank you once again.
You're welcome. Thank you, Brooke.